Now, the next example that I want to give, it introduces a little bit of confusion. And I'm not going to resolve this confusion completely, but I'm going to try to get you used to it. I'm going to take the average height again. But now with respect to arc length, which is usually denoted theta. Now, this brings up an extremely important feature of averages, which is that you have to specify the variable with respect to which the average is taking place. And the answer will be different depending on the variable. So it's not going to be the same. Well, I can't spell the word length here, just like the plural of witches last time. Well, we'll work on that. We'll fix all of our... That's an ancient Gaelic word, I think. Lenk or something. Okay. All right. So now let me show you that it's not quite the same here. It's especially exaggerated if maybe I shift this little interval dx over to the right-hand end. Then you can see that the little portion that corresponds to it, which is the d theta piece, has a different length from the dx piece. And indeed, as you come down here, these very short portions of dx length have much longer portions of theta length. So that the average that we're taking when we do it with respect to theta is going to emphasize the low values more. They're going to be more exaggerated. And the average should be lower than the average that we got here. So we should expect a different number, and it's not going to be pi over 4. It's going to be something else. And whatever it is, it should be smaller than pi over 4. Now let's set up the integral. The integral follows the same rule. It's just 1 over the length of the interval times the integral over the interval of the function. It's the integral, but now where does theta range? This time theta goes from 0 to pi. So the integral is from 0 to pi, and the thing we divide by is pi. And the integration requires us to know the formula for the height, which is sine theta, in terms of theta, of course. It's the same as square root of 1 minus x squared, but it's expressed in terms of theta. So it's this. And here's our average. Okay, sorry, I'll put this up here. So that's the formula for the height. All right, so let's work it out. This one, we have the advantage of being able to work out because we know the antiderivative of sine theta. It happens with this factor of pi, it's negative cosine theta. All right? And so that's negative 1 over pi times cosine pi minus cosine 0, which is negative 1 over pi times negative 2, which is 2 divided by pi. Just a second. And sure enough, if you check it, you'll see that 2 over pi is less than pi over 4 because pi squared is bigger than 8. Yeah, question. The question is, how did I get sine theta? And the answer is on this diagram, if theta is over here, then this height is this, and this is the angle theta, then the height is the sine. Okay? Another question.
I'm still just a tiny bit confused what that average means, first of all. And secondly, what would you say that this example 2 is with respect to the average? Is that x then?
Yeah, the question is, what is the first one? The first one is average of height of a point on the semicircle, and this one is with respect to x. So what this reveals is that it's ambiguous to say what the average value of something is unless you've explained what the underlying averaging variable is.
average height with respect to arc length is pi, or is 2 over pi.
Then the next question is, how should you interpret this, this value, that is, what came out of this calculation? And the answer is only sort of embedded in this calculation itself. So here's a way of thinking of it, which is anticipating our next subject, which is probability, which is, suppose you picked a number at random in this interval with equal likelihood one place and another, and then you saw what height was above that. That would be the interpretation of this first average value. And the second one is I picked something at random on this circle, and equally likely any possible point on this circle according to its length. And then I ask what the height of that point is. And those are just different things. Another question. Cosine of pi, shouldn't it be 0? No, cosine of, it's -1. Cosine of pi is -1. Cosine of, sorry. Yeah, no, cosine of 0 is 1. Cosine of pi is -1. And so they cancel. That is, they don't cancel. It's -1 minus 1, which is -2. Key point. All right? Yeah.
So I heard your explanation for why this value should be smaller than what we got in the previous, but I don't think I quite understood the logic behind it. Could you just repeat it briefly?
All right, let me repeat. So the question was to repeat the reasoning by which I guessed in advance that probably this was going to be the relationship between the average value with respect to arc length versus the average value with respect to this horizontal distance. All right, and it had to do with the previous way this diagram was drawn, which is comparing an interval in dx with an interval in theta, a little section in theta. And when you're near the top, they're nearly the same. That is, it's more or less balanced. It's a little curved here, they're a little different. But here it becomes very exaggerated. The d theta lengths are much longer than the dx lengths, which means that the importance given by the theta variable to these parts of the circle is larger relative to these parts. Whereas if you look at this section versus this section for the dx, they give equal weights to these two equal lengths. But here, with respect to theta, this is relatively short and this is much larger. So as I say, the theta variable is emphasizing the lower parts of the semicircle more. That's because this length is shorter and this length is longer, whereas these two are the same. It's a balancing act of the relative weights. I'm gonna say that again in a different way, and maybe this will. The lower part is more important for theta. So the question is, but shouldn't it have a bigger value because it's a longer length? Never with averages. Whatever the length is, we're always dividing. We're always compensating by the total. We have the integral from 0 to pi, but we're dividing by pi. Here we had the integral from -1 to 1, but we're dividing by 2. So we divide by something different each time. And this is very, very important. It's that the average of a constant is that same constant regardless of which one we did. So if it were a constant, we would always compensate for the length. So the length never matters. See, if it's the integral from 0 to 1 million, or 100, let's say, 1 over 100 c dx, it's just the same. It's always that c. It doesn't matter how long it is because we compensate. Right, that's really the difference between an integral and an average, is that we're dividing by the total.